Let's talk about nuclear reaction on page 10. Right now, I will want you to pause the video, read, and try to work on this part. Okay, so the three question, 1, 2, 3, three question or three session by reading these 2 pages on your textbook. Pause the video and do it now. Okay, so here are the answers that you should find from the textbook. So first of all, the fuel that we use nowadays in the nuclear fission power plants is using uranium. Be careful, one thing is that, in terms of nuclear reaction, there are 2 kinds. One is called fission, another kind is called fusion. We talk about it in year 9 when we talk about energy. And if you try to recall that, fusion is to combine the different things. The word fusion itself is combining things, and for fission is to separate things. So for physics, in uranium, we are trying to split it into a smaller atoms basically. And so for fusion, we could use hydrogen to combine it to helium. And that will be the reaction happen. However, for fusion, there is no power plants so far made by us, made by human. That is really possible to work on Earth. So if you can build one fusion power plant, and that using hydrogen to run, I'm 100% that you become a billionaire and you get Nobel Prize also, because this is something that has been studied for very, very long time, and people can't make it. And there are several reasons. I don't think I should spend too much time here, but then if you're interested, you should go Google or YouTube. There are some other videos explaining how come this is not successfully made so far. However, the thing that we could do is nuclear fission, and we will be using uranium. However, for uranium, it is very limited on Earth, so that's why other than the technology to build a power plant is difficult. Finding out the resources, the uranium ingredient you may call, is not easy. So that's why for some countries they may not have it, or it's too expensive to build one and also use the fuel. For there are 2 special components other than the power plant itself. Power plant itself is actually quite similar to fossil fuel power plant. If you remember in year 9, they simply burn the coal. In this case, for us, this nuclear power plant, the reaction take place, and then the heat will be generated from the reaction, and they will heat up the water. The water would become steam, and the steam will drive the turbine. So basically it's the same idea as the fossil fuel power plant. However, there are 2 special things for the fission power plants that we need to, so that it can maintain a good status. So the first thing is called control rod, and you may find the material is boron, cadmium, and the function of that is to absorb the neutrons, so that we can lower the reaction rate. Okay, so there is a simulation I'm going to show you in a second, but let me talk about moderator first. So moderator is usually using water or graphite to make the moderator. So basically it's everywhere, and the function of that is to slow down the neutron. So be careful, there are 2, it is actually different. Absorbing neutron and slowing down the neutron are 2 different things. Absorbing means it's literally absorb and the neutron got zero kinetic energy. Slowing down is just to reduce its kinetic energy. And by reducing its kinetic energy, actually that would make the reaction possible. Because when we have the reaction, the neutron may be too fast usually. And so if we make it slower, actually that helps the reaction to happen. I'll explain to you in the simulation right now. So what you can do is, I'll put down the link in the description, and you may download this simulation, which after you open it, it looks like this one. Okay, so let's take a look here. I'll try to do a demonstration to you, and if you want to try yourself, I will really appreciate you try it by yourself also. So here let's take a look of the middle. Here is a uranium atom. As you can see, the red and white are basically representing the proton and neutron. And there is a gun here. People usually say it looks like the one from the Toy Story, the Buzz Lightyear, right? The gun, but then actually this gun is to shoot out, as you could see, a white thing, which is, if you look at the legend, is a neutron. Let's take a look again. So what happened is, once I click this one, and then it will become 236. Okay, let's take a look again. 235, all right, and then you can see they absorb it, become 236, and then they will split. Okay, so this is what happened. And if I'll try again. If I try to do it in a slow motion, okay, so now 236, and then take some time, and then you can see it's split, and you can see there will be some energy produced. Most importantly, there are 2 daughter nucleus, and there are 3 neutrons. Okay, and this is what fascinating us the most, because if you think about, we are having many of these uranium-235 in a chamber, then these neutron will be able to go for other uranium, so you don't have to keep shooting from this gun, and then you can have this reaction going forever. Let's take a look here. So we have let's say the full chamber with 100 nuclei of uranium-235, and then once I shoot it, let me try it. 3, 2, 1, go. And it's amazing to see, like how it's like fireworks. Alright, it's so beautiful. I want to see it again. Alright, very amazing, isn't it? However, if you have some 238, alright, or I just simply take away all the 235 first. If you have 238, what happened to 238 when you shoot a neutron? Is it becomes 239. Right, and nothing happened. It become stable basically. So 238 is something that we don't actually prefer so much. I mean, in terms of producing energy. However, when we try to get it from the nature, the uranium is not pure always. Actually, the uranium-235 has a very limited amount when you try to find it in the cave. Right, people try actually, find uranium in the nature from a cave usually. It has a lot of 238, so that's why there's something to do with the purity of the material itself. So that is something to do with chemistry, of course. But anyway, if we have a mixture of this, then you can see that the reaction may not be as fast, but then still kind of being able to maintain for a certain time. So okay, here is more a confined space. Let's take a look. Yeah, so that's more like how it looks like. Okay, if you go for a third tab here, I'll encourage you to try it as well by downloading the simulation. Here you can see on the this green thing is like the control rod adjustment. Just now we talked about control rod already. Here, control rod here, and is to absorb the neutron to lower the reaction rate. Let's take a look. If we simply lower the control rod like this, and then we fire the neutron, take a look at what happened. Apparently this is problematic. Do you know why? Because you can see there's a, like, this is a representation, of course. I mean, people don't actually put a liquid in glass thermometer in it, but then this is representing the temperature. You can see that just now, maybe I'll try again, the temperature actually rise so quickly, like now. Wow. That will literally melt the whole container, and that is why we need to have the control rod to maybe move around or absorb the neutron during the reaction. So maybe I'll try to show again how it might be able to do like function properly. So let's say now, okay, if the temperature is too high, then you can see I can try to block it by and then absorb the neutron, and then the rate can still be going on. Oh, actually, I think I do too much apparently, but I hope you get the idea that you like by adjusting the control rod, by absorbing suitable amounts of the neutron, then it can be controlled. The rate can be controlled. And of course, in the reality, there isn't a guide to adjust this manually, like playing a mini game or every day. No, it's actually controlled by computer, of course. So using that can help us to adjust the rate so that it's maintaining safe. Here's a picture of how the control looks like. So it's really like several like rocks here, and then you can go up and down, and then that's how we can control it. For the moderator, which just now we talk about, is actually within the whole container. So this basically everywhere, the whole like maybe water is everywhere like this within this container. Okay, so make sure you try this simulation. In order to get you to understand even more quantitatively, I would like to introduce you one equation, and the most famous equation in physics. I'm sure before you study physics in year 9, you should have heard about it, and that is E equal mc squared by apparently Einstein. And I think if you even if you're not going to study physics in the future, it would be very nice that you can now, after you learn this, you can explain to other people like what is this equation basically. So here's an example. I would like to work it out with you, and in fact the use of E equal mc squared is not required in IGCSE. So if you feel too difficult, actually it's very simple. Alright, trust me. But then even if you can't work it out and somehow that's fine. Don't worry about that too much about the exam. It's really about appreciating what people find out, what Einstein find out in physics, and that actually help us a lot. Think about that. The nuclear reactor has been providing us a lot of energy nowadays for the city. So you're actually getting benefit from people's in the past, their hard work. So maybe try to understand, take a few minutes to understand how actually it works. So there is a question in page 255 in your textbook, which is in the PDF, or if you go to this page, you'll find this yellow box. There is a question here, but then I would not ask you to do this question. What I want to do is there are some information about their mass, and also there is a reaction equation which you can see uranium, Ba and Kr, and N is neutron over here. And what I will tell you to do is give you some hints. So how E equal mc squared work is actually you have the equation E, let me just write E equal mc squared, and in fact this is not a complete equation. There is something more, right, to add on, but then for now what you could do is simply is, in fact, E is energy, and m is mass, and c is speed of light, and speed of light is 3 times 10 to the power of 8. Okay, so what happened is we actually find out it's Einstein actually find out the mass of the reaction actually does not conserve. What it means is, normally when you study in any kind of physics, chemistry, biology, chemical reaction, we find actually one thing: conservation of certain thing, conservation of mass, conservation of charge, conservation of momentum, if you remember what we learned, conservation of energy, right? So that means whatever happened before and after, the mass, the charge, momentum, energy should all be the same independently. However, one strange thing that we find out experimentally is that the mass actually does not conserve. So some mass somehow on the right hand side is gone. So that means on the left hand side is somehow heavier, and on the right hand side is somehow lighter. So what happened to those mass? And after a long time of study, we find out again, Einstein find out that it is actually the mass delta m. That's why we have delta m, change of mass, change to the energy. That's why we have the enormous energy released from the reaction. So what you have to do in order to calculate the amount of energy in the uranium reaction is simply finding out the delta m. That means finding out the change of mass. So this is the first step I would recommend you to do. This is a hint. And after that, in order to find delta E, you just have to multiply c squared. Again, c is this one, 3 times 10 to the power of 8 meter per second. Is already in SI unit. So after that, you can find the amount of energy in the SI unit of joule. Okay, so I think that's all you need to know, and you may want to pause the video and try it now. Okay, so here is the answer. So I'll guide you step by step. So first of all, as I said, you have to calculate delta M, and you can see on the left hand side there's uranium, 1 neutron. On the right hand side there are actually, well, these two things of course, and also 3 neutron. So if you try to, do it in a bit more smarter way, I should say, then you could simply say that on the right hand side there are 2 neutron. Okay, in terms of mass, of course. So what you could do is this is uranium. See the 390, that one, minus these two, Ba and Kr. These two, you can see I put a minus here, and then minus 1.6 something. This one, this is neutron times 2, because again there are 3 on the right, 1 on the left, so actually there are only 2. You have to minus. And then the whole thing times 10 to the power of negative 27, because of, you can see the order of magnitude here. I just do it at once. At the end, you will find out the change of mass is 3.1 times 10 negative 28 kg. This is in kg, so it's all good. And as I said, what you have to do afterwards is just to multiply it with c square, speed of light square. So 3 times 10 to the power of 8 square. And then you should be able to find the energy here. Okay, please try to double check my answer. I maybe did it wrong, maybe just by mistake press the calculator wrong. So help me to double check the answer, let me know. So here is a further question to get you to understand the idea of how much energy it is. Because if you look at the energy here, it doesn't look like anything significant. If you think about it, this is not even 1 joule, right? If you think about like how what you learn in year 9, let's say if you got an object that is 1 kg, you can easily find something that is 1 kg. Like let's say maybe 2 textbook is about 1 kg. Like your math and maybe physics textbook put together is like 1 kg. And what you do is if you try to lift it for 1 meter, and then that will require some GPE, right? GPE, and that is mgh, and in that case that would be at roughly 10 joule already. And you can see that, hey, that's already 10 joule. So would this be so useless then? All right, if you think that way, then apparently you'll be wrong, right? Because this whole thing, our calculation right here, is referring to 1 single uranium. Okay, 1 single uranium, because if you look at this equation, it's really just one of them, right? So in reality there will be much more. Think about this. If you have 235 gram of uranium, which is not a lot, 235 gram is like 3 apples, right? Roughly, all right? It's not really a lot. And in fact, if you study chemistry, then you know when we say uranium U235, that actually means that it is 235 gram per mole. Mole is an idea you learn in chemistry probably, that is simply having 6.02 times 10 to the power of 23 that many of particles, and that would equal to 1 mole. Okay, so that means no matter if you don't understand, that's fine. That means at the end of the day, if you have 235 grams of uranium, that actually means you have that many of uranium, right, in terms of number. So what I mean is, since this is the energy for one single reaction, then you could, if you have 1 mole, that means 235 grams of uranium somehow, then you could have times this one, right? Because this is how many uranium you have. At the end, the energy will be 1.6 times 10 to the power of 13 joule, and that will be much more. Think about that. Again, the mass, in terms of mass, is not a lot of uranium. Think about like how people generate, like maybe for a car fuel, you have to refill a lot. I mean, if you have seen people refill the car, every time it's more than like a few liter. Talking about like a few liter really. So here is not even a lot. So again, you may not really catch the idea of, so how much is this energy be then. So think about this. If you have aircon may be having the input power as 2000 watts. I hope you still remember what this is. That means each second, joule per second, you spend 2000 joule in each second. So how long can you turn on this aircon, right, if you have such uranium, and of course assuming there's no energy loss, you just obtain all the energy from the reaction itself. Then what you could do is simply by using a very simple calculation, power equals to energy over time. Power is 2000 and energy is what you calculated here, and you will get the time that is 8.4 times 10 to the power of 9 in second. And again, you may not understand, I would not understand what that means too, so I converted that to years, and the final answer is quite amazing, that it tells you you can turn it on for 606 years. That means if you have that much of uranium, maybe somehow you just happen to go to those cave and I don't know, somehow you find it out, you dig it out, and if you could turn it into energy by doing the nuclear reaction, then you can actually have the energy to power up the aircon for that many years. Right? You can even use it for your whole lifetime. So that would be a lot of energy within a small amount of mass of uranium.